Good morning everyone, my name is Tan Yishan. I'm leader from Group 7. In this video, we will talk about our Computer Architecture and Organization project. So what is this project about? You can see the slide. For the part A, we will write 4 paper reviews which are related to computer architecture and organizations. And the part B, we will do a simulation project which is in front of the charger size in Unit processor. And we will configure a system with the architectural characteristic. And the part C, we will create a GitHub repository and committing a text file. And for the last one is the conclusion part, and we will talk about the difficulties and benefits of this project.
Thank you, Yishan. Now, I would like to present part 8 of our project, the review of 4 academic papers related to computer architecture and organization. In this part, we read and analyze 4 research papers that help us deepen our understanding of the development and core component of computer architecture. The first paper we review is titled A Study on Instruction Format on Computer Organization and Architecture. This paper mainly discusses how instruction formats are structured and function within computer systems. It explains the role of the CPU, especially the control unit, arithmetic and logic unit, ALU, and memory management. We learn how the CPU decode and execute instructions and how these core components work together to process data effectively. The second paper is Evolution of Computing. This paper provides a historical overview of computing development, trans transition from vacuum tube computer to modern devices, such as transistor, integrated circuit, Moore's law, graphical user interface, and mobile technology. This paper also shows how architecture evolved to meet societal and practical needs. The third paper is a high-accurate multi-objective ensemble exploration framework for design space of CPU microarchitecture. This paper introduced multi-objective ensemble design space exploration, a framework for CPU design optimization, which uses machine learning to improve prediction accuracy. It reduces time and resources needed for design space exploration, balance performance and power efficiency, and demonstrate how AI technically can be applied in CPU architecture design. The fourth paper is the analysis of how the bus system works on the von Neumann architecture. This paper extends the bus system in von Neumann architecture focused on data bus, address bus, and control bus. It also describes how buses coordinate communication between CPU, memory, and input or output device, compare older vs newer bus standards, and highlight the importance of bus system in system performance. By conducting this paper review, we gain several key benefits. Firstly, we develop a deeper understanding of the essential components and operational mechanisms of computer architecture. Secondly, the review process strengthens our research and critical thinking skills. For example, in the third paper, we saw how machine learning can be innovatively applied to hardware design. That's all from me. Now I will pass the mic to Yuling.
Thank you, Huiying. Now I will present about Part B, SMP Cache Simulation and Analysis. SMP Cache is a cache memory simulation tool designed for analyzing how different cache configurations affect system performance. It supports both uniprocessor and multiprocessor environment. We use it to stimulate miss rate and total cache replacement across different cache block size, ranging from 1 to 512. In our project, we test several threads files, including cexp.prg, comp.prg, swm.prg, and so on. For each file, we run simulation with varying block size and collected 2 main data points, the miss rate and the total number of replacement. Then, we use Excel to visualize and analyze the threads. One example is the thread file cexp.prg. When the block size was 8, the miss rate was 14.065%. But when the block size increased to 16, the miss rate dropped significantly to 1.54%. And after block size 128, the miss rate stabilized at around 0.74%. The other example is the thread file hydro.prg. When the block size was 8, the miss rate was 28.068%. But when the block size increased to 32, the miss rate dropped significantly to 18.195%. And after block size 256, the miss rate stabilized around 14.386%. This example shows that once the working set of the program fit into the cache, the number of capacity and conflict miss drop sharply, and only compulsory miss remain. Overall, From all the simulation, we observed that as cache size increase, the miss rates decrease. However, after a certain point, the improvement become minimal. Each thread file had different memory access pattern, so the improvement point were not the same. Through SMP cache, we were able to understand how cache size, block size, and program behavior impact overall system performance. That's all for me. Now, I'll pass the mic to Kersin.
Thank you, Hui Ying. So, we have successfully created a Git repository named TAO123_1A_group7 using GitHub Desktop to manage our group project collaboratively. First, the importance of source code version control in collaborative work environment with Git is version tracking. Every code modification is recorded with metadata, who made the change, when and why. So, next one is collaboration and team coordination. Through branches, team can work on feature, bug fixes, or experiment in isolation and then merge them back. After that is open source and community development. Git is essential for open source collaboration, allowing developers from around the world to contribute efficiently. From low levels such as assembly language and C, team size often small but crucial at depth. For high level like Python and Java is often large team with distributed responsibility. Using Git in collaborative work environment is non-negotiable for maintaining quality, enabling teamwork, and ensuring long-term sustainability of software projects. Thank you.
After completing this project, our team gained valuable knowledge about computer architecture and its applications. Paper reviews gave us insights into recent developments, improving our understanding of related topics. Using the SMP charger simulations, we examined how charger size affects miss rates in a unit processor. Trace files analysis confirm theory and show the balance needed for system optimizations. And using Git and GitHub taught us the importance of collaborative tools and improve our workflow. So despite challenges like setting up the simulation and planning meetings, we gained technical skills, teamwork, and project management experience. These projects enhanced our academic understandings and gave us valuable practical experience. This all for us. Thank you.